All right, here goes our intro to probability. Our warm-ups, how many possible outcomes are there when you flip a coin? Pretty simple. 2. Either you get heads or tails. Unless you have a 3-sided coin, which is weird, I've never seen, please show that to me. If you flip a coin 30 times in a row, how many times would you expect to get heads? We're thinking 15 out of 30, or I guess just 15 times, because it's 50% chance that we get heads. And we'll talk more about that later. Probability. It's the measure of the likelihood of an event happening. Long-term proportion with which a certain outcome is observed. So over time, what we should get. Experiment is a process with uncertain results that can be repeated. What is the law of large numbers? As the number of repetitions of a probability experiment increases, the proportion with which a certain outcome is observed gets closer to the probability of the outcome. So the more times we do it, the more times we really get to the probability that we should have. Things happen, the world's not perfect. If we flip the coin 30 times, we may not get 15 heads. Most likely we will not. Our sample space, a list of all the possible outcomes. Not the number of possible outcomes, but a list. For example, flipping a coin, it's either heads or tails. Rolling a die, it's 1, 2, 3, 4, 5, or 6. An event is a collection of all outcomes. A complement of an event, given if our event is E, it's E to the C, or E with a bar over it, meaning every outcome in the sample space that is not an E. Basically the opposite of E. So probability of not getting E. Which we'll see that the probability of E equals 1 minus the probability of not E. Well, duh, either you get E or you don't. They have to add up to 1 or 100%. The probability of an event is less than or equal to 1 and greater than or equal to 0. We can't have a probability less than 0. Can't have negative probabilities. That doesn't make sense. And it can't be greater than 1 because, again, we're talking in percentages or proportions, and we can't have over 100%. No matter how hard you work, you can't work 110% like those athletes tell us. The sum of all the probabilities of all outcomes must equal 1. So there's a bunch of different things. Then the probability of each one added up equals 1. Probability of getting heads is 1/2. Probability of getting tails, 1/2. So 1. It's only 2 options there. Probabilities can be written as fractions, simplified always, decimals, or percentages. Doesn't matter to me which way you write it. What is a probability model? A list of all the sample space with the probability of each one happening. So rolling a die. Well, we have 1, 2, 3, 4, 5, or 6. You can get one of those things. Die has 6 sides. The probability of that happening is 1/6 for each of them. As long as it's a fair die, we're not cheating. And again, all those add up to 1. Flipping 2 coins. We can get heads and heads, heads and tails, tails and heads, tails and tails. So if we're looking at the number of heads, we can get 0, 1, or 2. If we get, what's the chances that we get 0? Well, that guy right there. So 1 out of 4. Probably that we get 1 head, these 2, so 2 out of 4, 1/2. And well, the last one has to be 1/4, add up to 1, but it's also one way we can get 2 heads, just getting 2 heads. What does it mean if the probability of an event is equal to 1? Well then, obviously, it's going to happen. It's a 100% chance that it's going to happen. Because 1 as a percent is 100%. So it means it is a certain probability of me falling out the window after trying to fly is 1. I'm not flying anywhere. What does it mean if the probability of an event is 0? That means it's impossible. Probability of me jumping out the window and flying is 0. I can't fly. Not without a plane. There are two approaches for probability. Theoretical, what should happen, which is what we usually know, number of ways E can occur over the total number of possible outcomes. Experimental is the frequency of E, or how many times it actually happens. This is reality over the number of times that you do something. And what does a large number say about these two types of probability? It is closer to being the same as the experiment. So if we do it enough times, those two numbers should be the same. They might not be if we have small events. For instance, if I'm spinning a spinner, there are 4 colors. They're all equal. So we have a 25% chance of getting each of them. But if I spin it 10 times, we're going to see, it didn't happen equally. We got 40%, 20%, 30%, and 10%. 4 blue, 2 pinks, 3 grays, 1 orange. But if I do it again with a bigger number, 100 spins, it's getting closer. 20%, 30%, 20% is the farthest one away. I guess 30% is either as well. What if I do it 1,000 times? It's even closer. These are a little bit off. It's not going to be perfect, but out of 1,000 spins, we got pretty close to what we want. We should have 250 pink, and maybe we can even add some more. Another 1,000, and getting even closer. Another 1,000. We're getting really darn close. Pink still comes up a little bit more often than we expect, but the other ones are almost exactly at 25%. We're getting there. So that's what the law of large numbers says. As we keep doing it and getting closer and closer to a bigger number, those values are theoretical, what should happen, and what's actually happening become the same thing. A tree diagram is one way to list and find all the outcomes of an event. So suppose we're flipping a coin 3 times. Well, there's 2 options. We get heads or we get tails. And then we flip again. We still have heads the first time, and we get heads again, or we get tails. If we get tails the first time, we get tails and heads, and tails and tails. And we do it again. That's flip 1, 2. Now flip 3. Heads, 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 tails, heads, tails, heads, tails, tails. Run out of room here. We can get tails, heads, heads, tails, heads, tails. And the last one, we get tails, heads, heads, and tails, tails, tails. Those are all our options. We have 8 options for this. So what is a sample space? It is all of those. We can get 3 heads. We can get 2 heads and then a tail. We can get a head and a tail and a head. Different than this last one, just because of the order. The same number of tails, yes, but the order is different. We can get heads, tails, tails. We get tails, then 2 heads. Tails, heads, tails, 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 heads, and tails, tails, tails. So that is our sample space. All 8 options. Our sample space is the number of options. What can happen? Was the probability model for the number of heads? So now we're just looking at the number of heads. Well, we can get 0, 1, 2, or 3. We know all of these add up to 1. Well, how many times did we get 0 heads? Just the 1 time that we got all tails. So that's 1 out of the possible 8. How many times can we get 1 head? Just exactly 1 head. This guy and this guy. Oh, and this guy. So 3 out of 8. What about exactly 2 heads? We get here, here, and here. Again, 3 out of 8. And those are simplified. You cannot simplify those anymore. And again, 1 minus all 3 of those should give me the last one. How many times we can get 3 heads, but there's only 1 way, there's only 1 left. So it's 1 out of 8. And that's our probability model. List of all the possible outcomes, for the number of heads in this case, and their probability. And then we can work with that. All right. Flip a coin 30 times and record your results in the frequency table below. We thought from our warm-up we should get 15 heads. And then 15 tails, of course. It only makes sense. So if we go flip our coin 30 times, we have our ratios down here. Looks awesome. It takes a while. It's a nice coin though, at least. So we got 11 and 19. Was it exactly 15 and 15? No. Is it that even? No, not really. So we had, I can't remember which one we're looking at, 11 heads and 19 tails. So is it perfect? Did you get exactly 15 heads? No. Because theoretical and experimental probabilities are not the same. What we expect and what happened is not exactly the same. If it was, we'd all go gambling and win a bunch of money. But as n gets closer, as we keep increasing, we keep doing this experiment, should we get closer to 50%? So let's make this 3,000. I guess they won't let me do 3,000. We'll toss it 1,000 times. What do you know? These two are much, much closer. We should be getting 500 of each. I guess we've done 1,030, so we should get 515, and we're only 10 apart each way. Not too bad. So we're getting close to our 50% on each of those. All right, some more examples. Suppose the bag contains 5 red marbles, 8 blue marbles, and 7 yellow marbles. What is the theoretical probability of the student reaching into the bag and pulling a yellow? Well, how many different yellow marbles are there? There's 7 out of the total marbles that we could pull. 5 plus 8 is 13, plus 7 is 20. We can't simplify that, so we can leave it like that. Or we can put it as decimal. That's fine as well. Or if you want a percentage. Doesn't matter. All mean the exact same thing. I believe it's going to be easier to work with a decimal answer here, and most of the time that's what I'll look for. All right, the student decided to conduct a probability experiment using that bag of marbles. They selected 1 marble at a time, replaced it after each selection. That's important, that we replaced it, or else the probability changes, and we'll talk about that in later sections. They recorded the results in the table below, use the table to determine the probability, or the experimental probability of picking a yellow. So it's the same thing, but now we have it in practice. So we have 12 out of, and all of these add up to, well, 8 plus 10 is 18, plus 12 is 30. We need to simplify that. So we can divide everything by 2. Oh, we can divide it by 3 as well. So we get 2 out of 5. Now it's hard to compare this with this because they're not the same denominator, so let's put it as a fraction. That's 0.04. Again, why we want decimals, it's easier to compare. Well, are they exactly the same, these two numbers? No. Are they somewhat close? Yes, and if we kept on doing this, it'd be even more. But life isn't perfect, so we get close to what we get. So which was greater? The experimental. So it showed up more in the experimental. Just because somebody else could do this and get a much lower number. I never know. Which of the following of the numbers could be probability for a simple event, for one little thing? -5? No. Probabilities have to be positive. 0? Yeah, means it's not going to happen, but it's still a probability. 3 out of 5? 0.6? Yeah, that's fine. It's less than 1. 8 over 3? Well, that's 2. And 2/3? No, because that's over 1. E? 1? Yeah, that means it's going to happen for sure. So whereas B was impossible, E was a certainty. It's gonna happen. All right, so we just keep finding our probabilities, see which ones work. 0.45 is fine. That's good. That's good. Circle the ones that are good. 75%. Yeah, that's fine. That's 0.7 is decimal. It's less than 1, greater than 0. Negative 8 point, no, negative anything. Not going to work. Can't have a negative probability. 2.7, no, because if we turn that into a percent, that's 270%. That doesn't make any sense. So that doesn't work either. Pretty straightforward. Quality control inspector samples 500 projectors and finds defects in 3 of them. What is the probability that an LCD projector chosen at random would be defective? Right, the probability is a fraction. And again, this is experimental because we've actually done something. So the probability that a fraction reduced to lowest terms, so chosen at random will be defective. So 3, because there's 3 that are defective out of 500. And we can't simplify that anymore. So that's it. We could write it as a decimal or percent, but there's a fraction, a little bit easier. Doesn't ask for more, not going to give more. Bag contains 5 blue, 8 red, 7 green marbles. Marble selected at random. Find the probability it's red. Well, that's 8 out of the total number of marbles. This adds up to 20. So it's 8 over 20, but that's not simplified. So we divide those by 4, we get 2 out of 5. Find the probability, the complement of red. Well, that means the opposite. A red complement, or we could write it like this. Well, it's all that are not red. So that's red, or that's blue and green. 12 out of 20. We can simplify that down to 3 over 5. We can see 3 over 5 plus 2 over 5 gives 5 out of 5, which is 1, and that's what it should be. A complement plus itself gives us 1. Probability not blue or green. Well, if it's not blue or green, it's got to be red. So, not blue or green. Probability of red, which we already found out was 2 over 5. Probability of green is 7 out of 20. Can't simplify that, so we leave it alone. And the probability of blue is 5 out of 20, which we can simplify to 1 over 4. And again, these can all be put into decimals. This would be 0.4. This would be 0.6. Now you can definitely see that these two add up to 1. 7 over 20 is 0.35. 1 over 4 is 0.24 or 25. And again, if we look at probably the blue, green, and red, 0.4 plus 0.35 is 0.75, plus 0.25 is 1, and that's all our options. They have to add up to 1. How does the probability of red compare to the probability of not blue or green? They're exactly the same. Because they mean the same. There's only 2 different colors, or 3 different colors. It's either red, or it's not red, so it's not blue or green. What is the sum of red, probability of red, green, and blue? Just like we said, 0.4 plus 0.6 plus 0.25. Well, that's not right. Probability of green is 0.2 or 0.35. And it equals 1. Why do we think that is? For all our options. Probability that you pull one of those is 100% or 1 because that's all we have. We don't have any other marbles there. There are 6 equally likely outcomes if a die with sides 6 labeled 1 through 6 is rolled. Make A is getting a number less than 4. B is an odd number. So before we draw our Venn diagram, what numbers are less than 4? 1, 2, and 3. What are our odd numbers? 1, 3, and 5. So our Venn diagram, we have our box. That's our sample space. We can label that S, so that's what all these outcomes should come in. And again, our sample space, 1, 2, 3, 4, 5, 6 are all our options. Now, if we're looking at A less than 4 and B, are there anything that they have in common? Yeah, they have these 2 in common. our Venn diagram is going to overlap. That's where 1 and 3 are. So if we let this circle be A and this be B, well, what's in A? What number happens in A that's not in B? Well, 2. So again, 1, 2, and 3 are still in circle A, but 1 and 3 are also in B. What else is in B but not in A? 5. Now, what are we missing? We have 2 numbers that don't apply here. 4 is not less than 4, and it's definitely not an odd number, so it's out here. And 6 isn't in either one of these. It's not odd, and it's not less than 4, so 6 is also out here. Now we just have to answer our questions. The probability of getting A. Well, how many options are there? 1, 2, or 3? 1, 2, and 3, I should say. So 3 out of 6, or 1/2. The complement of A means anything outside of the circle A. So that is everything except for that, including part of B. So what numbers does that include? Well, everything except for those. So 4, 5, 6. Also 1/2. And again, these two have to add up to 1. Well, 1/2 is 1. We're good. If we're looking at probability of B, an odd number, well, we have 3 numbers, 1, 3, and 5. What's 3 again? 1/2. Probability of not B, well, again, it's everything that's not in circle B. So it's all this, including this now, because it's everything that's not in B, everything outside of the circle B. And that's why Venn diagrams help us, make it a little bit easier to see. Well, how many numbers are not in B? We got 2, well, 1 and 3 are in B, 5 is in B, 4 and 6 are. 3 out of 6, 1/2. And again, double equal to 1, equal to 1, because the probability of A plus the probability of A complement equals 1, so does for B. Any event, probability of anything plus its complement equals 1, which of course only makes sense.